last Friday, so this shouldn't be too bad. Hooke's Law. What we did on our lab last Friday, remember we hung the different masses on and we graphed it and we found our linear plot. Okay, so when we talk about Hooke's Law, the force on the spring is proportional to the stretch or compression distance. This is for an ideal spring. Okay, so when I say an ideal spring, we know that it's going to obey Hooke's Law. A non-ideal spring can still be elastic. And when I talk about a non-ideal spring, a rubber band would be an example of a non-ideal spring. Okay, if we were to repeat the lab that we did last Friday with all of the different masses and then tried to plot force versus stretch distance for a rubber band, we would get a graph that would probably look like that instead. Okay, it's not going to be perfectly linear. So hence, if you're taking the AP exam, I can see the AP doing something like that, just asking a question. They could give you a graph like that for a force versus stretch distance and saying, is it an ideal spring and why not? Okay, it's not linear. Okay, I mean, that's as simple as you can make it. You don't have to get any more complex there. So, Hooke's Law is for an ideal spring when the graph is perfectly linear. Okay? The actual equation is force equals negative kx. On your equation sheet, and we are back to the pink equation sheets now. On your equation sheet, it just shows it as magnitude only. Don't worry about that negative. That negative is just to indicate that the spring force is a restoring force. The spring force will always try to get the spring back to its original location. I think that's pretty self-explanatory. So, long story short, if I pull to the right on a spring to stretch it, which way is the spring force? To the left, all right? And which law, Newton's laws, does that obey? That's the third. Forces are equal and opposite, okay? Does that make sense? Pretty straightforward. All right, unit is a Newton per meter, not Newton meter. Okay, Newton per meter for the spring constant. As long as we have an ideal spring, the spring constant is constant. It's the slope. All right, and a greater spring constant just means what? What's that going to indicate? It just means the spring's stiffer. Okay, it's going to be harder to pull it or push it. Does that make sense? So the greater the spring constant. So you'll see spring constants ranged anywhere from, I think, in our lab, if I remember right, some of your groups were around 5 on your spring constant. Whoever was at this lab bench, I think yours was around 70. You start talking about the suspension springs on your car, we're talking in the 80, 90,000 Newton per meter, okay? Obviously, those aren't very stretchy for a reason. It'd be kind of fun driving down the road hitting the bumps with that, but still. Make sense? Okay, force versus stretch or compression distance. We already talked about the slope is the spring constant. In your lab, I had you guys derive out the equation for the area. The area under the curve is the amount of energy stored in the spring. So if we look at this, we have 1/2 force times x. Why is it 1/2? That is called a triangle, okay? So 1/2 force times x. If we sub in force equals kx into the equation, we get an equation that says 1/2 kx squared. So the energy stored in a spring is equal to 1/2 kx squared. There's nothing wrong with using this 1/2 force times x. That's fine and dandy. It's going to give you the same answer. It's derived from the same thing. Okay, so technically, this equation is perfectly good. You can use it. But this is the one that's on the equation sheet. Okay, everyone good so far? Pretty straightforward. Okay, we will not be able to use kinematics as we currently know them. We can put in the next derivative of position versus time, and then we can solve for our kinematics equations doing that. Did you guys have to do that in calculus at all? Did you have to do the next derivative? That's the addition. That's jerk, which is your changing acceleration, and that would be your next derivative of that. So you can go through all those. So yeah, we can do this to calculate the time period for it to come off of a spring, but I don't think we're going to be doing that. Okay. Since forces are changing, there is nothing wrong. We can calculate instantaneous accelerations. We can still use Newton's second law for each point. Okay, we can say force equals ma. There's nothing wrong with that. But we can't use our kinematics equations because the equations that we have that we've been utilizing are equations of constant acceleration. So really the only way that we have to solve for any information with springs is to use energy concepts. Okay? So let's say I have this spring compressed, and we're going to say the unstrained distance is x initial. So we'll say we compress it negative. If I compress this spring negative, we're starting at a negative position, but if I release that object, I am going to have a graph that is a negative cosine graph. Okay, does that make sense? All right. Since velocity is the first derivative of position versus time, what is the velocity versus time graph going to be? Say again? Be a sine wave. So this is going to go here. Like that. I know those of you who haven't had pre-calc yet don't know what all the derivatives of those are, and that's okay. So this is going to be a sine. And what is the acceleration graph going to be, because it is the derivative of position or velocity? This will be a cosine graph. So here's what's going to happen. For today and tomorrow, we're just letting the spring launch the object. Okay? So our velocity graph will just continue to look like that. Right? Once it leaves the spring, assuming no friction, it'll just slide on. The next phase of this is leaving the object attached to the spring. And if the object stays attached to the spring, what's going to happen with that graph now? This one's going to go like that. This one's going to go here. And this one's going to go here. Okay? Really, in a nutshell, that's what we're going to be doing. I used to derive out the equations for velocity and acceleration, but I quit doing that last year because we were running out of time. Okay? It's actually very useful to have them. It shortens things down. Let's do this one problem here because I've got this a step harder than what's on your problem set so that we can kind of talk about it. They can get really complex if I want them to, folks, okay? Thinking about energies sometimes gets a little